let's continue our discussion. But before that, let me summarize what we have discussed in the last video. So we started our discussion about equilibrium of a rigid body. So a rigid body is said to be in equilibrium if linear acceleration as well as angular acceleration is zero. That is, linear momentum and angular momentum, these two are constant. There is no change in linear momentum as well as angular momentum. And this will happen when net force acting on the body or rigid body is zero as well as net torque is zero. And here we are talking about external because we have discussed this thing that internal forces and torques are not going to give any change in momentum. Okay. So one thing is here, force is this total force means sum of all the forces. If n number of forces are acting on the rigid body, so here we can write them in short form with this summation sign. So these forces are independent of choice of origin. This is a known fact. What about this torque? Because this torque includes the position vector, which varies with changing origin. So this thing we are going to discuss. Because in case of single particle, this torque or the moment of force will be r cross f. And if we are changing this origin, this r will be changed and hence this torque will be changed. So will it be happening in the case of rigid body? This thing we are going to check. But before that, let me discuss a little bit more. So these two equations are vector equations. We can resolve this force, net force here, into its three components along the three axes, as well as we can resolve this net torque also into three components, and then we can get scalar equations here, which are easier to solve. Now, we also discussed about partial equilibrium. So there may be a body in rotational equilibrium only or translational equilibrium only. And here we have two different situations elaborating these two things. So let's say we have a rigid body, two forces are acting along the same direction and they are equal in magnitude. So net force is not going to be zero. There will be some acceleration, there will be change in momentum, but net torque is zero in this case. In this second case, net force is zero. Two forces are acting which are equal in magnitude and opposite in direction. So the net force is zero, net acceleration will be zero, and change in momentum, linear momentum will be zero, means linear momentum will be constant. But there will be rotation in this body as you can guess here. So net torque is not zero. So this is partial equilibrium, means a kind of translational equilibrium. And these two forces are acting along different lines. So here, look, this force is acting along this line and this force is acting along this line. If they are acting along the same line, again, net force along with net torque will also zero. So here in this case, net torque is something. Let me carry forward this situation. So here we have the body and this is force acting here in this direction and this is force in this direction. Okay, so there will be torque. And if we are talking about torque about this point, let's say this is a point about which we are going to say what is the torque of this body. So due to this force, there will be torque here, and due to this force, there will be torque here. And this torque, we can find out direction. If we are taking a position vector here, let's say something d1, and from here to here, position vector something d2, we can say torque here, r cross f will be, d1 cross f will be outward. So let's say the torque here, tau1 will be pointing outwards here. And in the same way, we can find out what is the direction of torque here. So let's say this is tau2. This is also pointing outward. So what is happening? Two equal and opposite forces acting along different lines are producing torque in a body. So this is also torque, and that's why now you should be convinced that torque is also called couple. So in this case, we can say couple. Now, let's get back to the question we have arised here. Whether the net torque in case of a rigid body will be independent of choice of origin or not. So we are going to discuss this thing. Okay, let's continue with this particular scene and I'm redrawing it with some different notation. So let's say this is first point where this force is acting and this force, let's say it is F1, and this is second point where this force is acting, let's say this is F2, and this is position A and this is position B. So this is F2 and F1 is minus F and F2 is F. These two forces are equal and opposite in direction. Now, we are choosing random origin here, and the position vectors for this point 2 will be, let's say this is R2, and for this point 1, let's say this is R1, and then there is a vector here AB. Now, if we want to know what is net torque, so the net torque will be sum of these two moments of force. How? This is, let's say, tau 1, and this is pointing outwards, and this tau 2 is also pointing outward. So we can just sum these two torques, tau 1 plus tau 2, and then we can get what is tau 1. This will be R1 cross F1. So R1 cross F1, and tau 2 is R2 cross F2. And F1 is just acting opposite to F2, and we have chosen this direction to be positive for vectors, so this direction is negative. So this is minus F if these two forces are equal. So this is, let's say, minus F, this is F. So we have here minus R1 cross F plus R2 cross F, and we can take this cross F common, and then we will have R2 minus R1, and this R2 minus R1 is nothing but this vector AB. Here we can see easily the position vector R2 minus position vector R1 is the displacement vector AB. So no matter where we are shifting our origin in this case, whether we are choosing another origin at this point, this vector AB is not going to change as long as we have fixed these 2 points. So we can say the torque on the rigid body is independent of the choice of origin. Now let's move to the next topic, and we are discussing about now principle of moments. So principle of moments. Okay. So let's take a situation here, then we will clearly understand. Let's say we have a rigid body here, and there are two forces acting on this body, F1 and, let's say, here F2. And let's say there is a point here about which net torque is zero, and at this point, let's say there is a normal reaction here. So if this body is in equilibrium, net force on this body will be zero, as well as net torque will be zero, and we are going to obtain torque about this point. So let's say this is position vector R1, and this is position vector R2. Okay, so what we have now, net torque as well as net force on this body is zero. For translational equilibrium, net force will be zero. That is, forces acting downward and force acting upward, they should be equal in magnitude. So R equals to F1 plus F2 here. And now, second thing, torque. Due to this F1, let's say it is tau 1, and you can find out this torque is pointing outward, means outward from this screen. And in this case, the torque, let's say this is tau 2, this is pointing inward. We can write the magnitude of torque 1 should be equal to magnitude of torque 2. And what is the magnitude of torque 1? R cross F. And this is, let's say, 90 degree, and this is also 90 degree. So we can say R1 F1 sine 90 degree, which is 1. So magnitude will be R1 F1. And in the second case, the magnitude of torque will be R2 F2. And then we can find out a special relation here. F1 by F2 equals to R2 by R1. And this ratio is known as mechanical advantage. Mechanical advantage. Okay. Let me little bit more elaborate this thing with example. How this mechanical advantage can be harnessed. Let's say we have a lever here, I'm taking the same situation. So, and we have placed a load of, let's say, 40 kg here. And this lever is pivoted at point, let's say, in middle here, exactly in the middle. So this point will be acting as fulcrum, and at this point, due to this way, yeah, due to this mass, there will be weight, and this weight will be kind of force, let's say F1 downward, which is weight of this body, and this will be 40 into 10 Newton. If we are taking G equals to 10 meter per squared second downward direction. And now we want to lift, or we want to keep this body here stable. So we have to apply, let's say this is F2, or we can say this is effort and this is load. Yeah, in case of lever, this is a kind of simple machine which we call lever, and an ideal lever is massless, not a practical one, but the mass of this lever is much more less than this load and effort. So this is load, okay, and this is effort to keep this load balanced. So what we can do, if, okay, one more thing here, the position vector of this point where the effort is being applied and where this load is pushing down. So let's say this is position vector R1 and this is R2. Okay, so we have this equation here, F1 by F2 equals to R2 by R1. So this length from this fulcrum is called, this R2 is called effort R, in this case of lever, effort R, and this R1 is called load R. This R1 is called load R. And now in this particular scene, if I am asking, okay, in this particular scene, if I am asking how much force should be needed here to apply, how much effort should be to keep this load balanced. So you can say easily F1 is 400 Newton, F2 we need to find out, and R1 and R2. If this is exactly in middle, let's say this length is R and this length is also R, then it will be R divided by R, and then you can say F2 should be, I'm writing magnitudes only here, we have discussed this thing, 400 Newton. So to balance a mass of 40 kg, that is a weight of 400 Newton, we need to apply 400 Newton. Now, how can we harness mechanical advantage in this case? How can we apply less effort to hold or to balance more mass or more weight here? So let's shift this origin or reference to a new position. And now the length of this load arm is R. That is, now we have reduced the length of this R1 to be R, and the length of this R2, that is effort R, we have increased so that it is 4R. Okay. Now I'm asking how much effort should be put here, how much force should be applied to keep this 400 Newton weight balanced. So you can say easily in this particular case, now we have 400 Newton divided by F2 equals to 4R divided by R, and then you can say 400 Newton divided by F2 equals to 4 by 1, or you can say F2 equals to 400 by 4, which is 100 Newton. So you have now understood why we are saying this ratio, yeah, this ratio to be mechanical advantage, because we have balanced a greater load with less effect. Okay, let's move to the next point. Now we are going to discuss about center of gravity. In short, CG. Okay, you may have balanced notebook or pen or pencil on fingertip. There, let's say you are balancing a marker on your fingertip. You are doing this thing by applying some force at appropriate location, While doing so, what you are doing, you are just applying a force on the center of gravity. So let me draw here an extended body in general, an extended body, and let me figure out what is the situation here. So this extended body is a system of particles, infinitely many particles. So let's say this is particle first having mass m1, then it will experience a downward force here due to this acceleration, due to this gravitational pull. It will experience a force m1g, and in the same way, all the other particles will experience the this kind of force, gravitational force. And if you are balancing this thing on the tip of something, okay, let me use another color. So if you are balancing something by applying a force at this point, and if this extended body is in equilibrium, equilibrium means rotational as well as translational equilibrium, then this point is center of gravity, where let's say you are applying a force R. So if there are n number of such particles, m1, m2 up to mn, okay, so for translational equilibrium, this R will be equal to m1. Yeah, in magnitude it is equal, and in direction it is just opposite. M1 plus M2 plus up to Mn into G for translational equilibrium. And for rotational equilibrium, all the moments of these particles about this point should be zero, means sum of those. So let's take some random particle here, ith particle, and the position vector is Ri. So we can say for rotational equilibrium, sum of I equals to 1 to n Ri cross F. F is Mi into G. So Mi into G. This should be 0. And now you can see this acceleration due to gravity is not 0. So I equals to 1 to n Ri cross Mi. And this Mi, M is nothing but scalar quantity. So we should not be bothering about this cross sign or this dot sign if there is. So we can simply write M into Mi into Ri equals to 0. And if this is the case, you can say that center of gravity coincides with center of mass. Yes, this is the condition when center of mass is at origin. And here the origin we have chosen, or reference point we have chosen, is nothing but this center of gravity. So this is the case when center of gravity coincides with center of mass. And now we can find out center of gravity for various regular shaped bodies by just finding their centers of mass. And we have done this thing earlier. We have already discussed so many centers of mass for various bodies. Then, is it always valid? Is center of mass always coinciding with center of gravity? So no, the answer is no. If there is a variable g, non-uniform g, means if the body is placed in non-uniform gravitational field where different particles of this body are experiencing different acceleration due to gravity, in this case, let me write first non-uniform. So in this case, center of gravity and center of mass will not be coinciding. Okay, so we can say in case of uniform gravity and small objects, we can say, or large object placed in uniform gravity, center of gravity coincides with center of mass, and this statement will help us to find out center of gravity in various cases where we know the center of mass of the objects. What about center of gravity of irregular objects where we have not obtained till now center of mass? So in case of irregular bodies or objects, let's say bodies, we can do a small experiment to find out where its center of gravity is located, and this is very easy. Only thing we need to do, we can suspend this body. Let's say this is the body. We can suspend by tying it to a string and in its equilibrium position, this string pulling it upward with some tension T, and this tension will be along a line, and on this line there will be somewhere center of gravity. Okay, so this is for one point here. We can just do the same thing for the body by tying it at another location, and then we can get another line of action of this tension. And with all those lines, wherever they are intersecting to each other, wherever there is a common point, that is the center of gravity for this irregular shaped body. So that's all for this video. In the next video, we will discuss few examples.